Evaluation of physical and mechanical properties of polypropylene and Cockle Seashell Composite. Abstract calcium carbonate is one of the most common fillers used in compounding of Polypropylene.Cockle seashell, a bioresource rich in calcium carbonate and readily found along the seacoast, wash grounded to fine particle size and sieved to obtain a mesh size of 150 micrometer. Cockle seashell powder was compounded with polypropylene, keeping the weight of polypropylene constant at 50 g while increasing the filler loading of seashell. Seashell powder was added to the polypropylene matrix ranging from 5G, 50G. The samples were prepared using a compression molding machine. 10 samples were prepared without compatibilizer and another 10 samples were prepared with maleic anhydride as a compatibilizer. A control sample of pure polypropylene was also prepared. The mechanical properties such as tensile strength, flexural strength, hardness, and elongation at break of the samples were analyzed. Tensile strength of PP/SS samples with maleic anhydride increased steadily and at PP/SS, 50/30ths, had the highest tensile strength of, while PP/SS samples without maleic anhydride had better elongation at break.PPcomposite incorporated with compatibilizer had low flexural values compared to PPcomposite without compatibilizer. However, there was no significant difference in the hardness property of the composites with and without compatibilizers. 1.0 Introduction. Polypropylene, PP, is a polymer obtained from the polymerization of propylene and regarded as one of the commodity polymers in high demand. It has found application both in technological and domestic end use. Technological reasons are often the basis for using particulate fillers in polypropylene, which gives a new material with enhanced properties such as improved stiffness and higher heat deflection temperature. 1 Fillers used in polypropylene are glass fiber, talc, or magnesium and calcium carbonate. 1. Calcium carbonate, CaCO3, is the utmost plentiful white mineral in the Earth's crust. It's white, odorless, non-toxic, soft, and has a low refractive index, and at temperature is stable across a wide temperature range. CaCO3 is a mineral filler which is formed in rock types such as limestone and chalk. 2. Calcium carbonate from biological waste such as seashells, cockles, scallops, marine mollusks, mussels, shellfish, oysters, and egg shells can be alternative fillers for polymer composites. They are discarded in large quantities by food processing companies. 3. Cockle is an edible marine bivalve mollusk which belong to the family of Cardiidae. They are found in sandy sheltered beaches throughout the world. 4. Cockle seashell, SS, is found on the beaches across the world and contain a significant amount of biocalcium carbonate. The amount of calcium carbonate present in cockle shell has been estimated to range from 92%, 98%. 5 to 9. Some researchers have employed biocalcium carbonate as fillers for thermoplastics such as polyethylene and polypropylene. Seashell treated with NaOH was used as a filler for polypropylene. The tensile strengths of the composites were compared with composites filled with mineral CaCO3. The PP/SS composite showed better tensile strength than the PP/calcium carbonate. 10. Low-density polyethylene, LDPE, composites were prepared using cockle shell as fillers. The LDPE composites with cockle shell had higher Young modulus value than the pure LDPE. 11. Improved tensile strength and hardness was reported for natural rubber filled with bio-CaCO3 by Nora's Lina et al. 12. This work aims to examine the properties of using CaCO3 from sea waste, designated as bio-CaCO3, as a replacement for synthetic CaCO3 to be incorporated into PP and evaluate the physical and mechanical performance of the biocomposites. The mechanical properties evaluated concentrated on the tensile strength, flexural strength, hardness, and elongation at break of the biocomposites. 2.0 Materials and methodology. 2.1 Materials. Cockle shells were obtained from Sultan Beach, Badagry, Lagos State, Nigeria. Polypropylene pellets obtained from a chemical company in Lagos was used. Maleic anhydride, Ma, of analytical grade was gotten from a chemical company in Lagos. 2.2 Methodology. 2.2.1 Preparation of the cockle shell particulate filler. The cockle shells were washed thoroughly with water to get rid of dirt, and oven dry at a temperature of 100 degrees Celsius over 2 hours. It weighs at that point taken to a grinding mill to be milled into small particles. The amount of cockle shell obtained was 20 kilograms and after milling, it reduced to 19.5 kilograms. The milled cockle shell was then sieved with a British standard sieve mesh to obtain a particle size of 150 m. 2.2.2 Preparation of the composite. The polypropylene pellets were first masticated with a 2-roll mill for about 5 minutes at a temperature of 110 oC, after which the cockle shell particulate filler was added and also masticated together for another 5 minutes. The temperature was kept constant until a fine homogeneous mixture was obtained. The mixture was allowed to cool for 24 hours. The mixture was then compression molded in a hydraulic press at a temperature of 160 oC for about 5 minutes. Paraffin wax was added to the mold. Before placing the mixture in the hydraulic press, 10 samples of compatibilized composites and 10 samples of composites without compatibilizer were produced in a dumbbell shape. The samples' mechanical properties were analyzed. Table 1, Formulation for Polypropylene/Cockle Shell Composite without compatibilizer. 2.3 Tensile strength and flexural strength. Mechanical properties of the blends were investigated using computerized universal testing machine, Instron Series 3369, with a load cell 50 knots ASTM D680/SM790. 3-point bending test was used to determine the flexural strength. The span length was 65 mm. The dimension of the specimen for the tensile strength was 70 mm by 5 mm by 15 mm. Table 2, Formulation for Polypropylene/Cockle Shell Composite with compatibilizer. Sample code. Polypropyl.Cockle. Maleic Anhydride, 2G. 2.4 Hardness Test. The durometer OS2H04081401 was used to determine the hardness properties of the blends. The durometer's indenter pin was placed very close to the sample on a metallic base. The durometer's load was pulled down to allow the indenter pin to penetrate the sample. On the display screen, the sample's resistance to indentation was measured, and the value was recorded. This was repeated 3 times for each sample, with the average value taken. From Figure 1, it can be observed that the tensile strength of the composites is lower at smaller filler concentrations. There was a gradual increase in the tensile strength values of the composites as the filler loading increased to 15 G relative to pristine pages. Optimal tensile strength, 14.64 MPa, was observed with the incorporation of 2 G of Ma into the composite PP, SS, 50:30, after which there was a decrease in the tensile property of the composites. Maleic anhydride addition to the composites increased the interaction between the polymer matrix and the particulate filler. Similar trend was observed by Mumu's amyl ETAL11. In this study, the tensile strength was significantly better than the control sample, pristine PP. Figure 2 shows the flexural strength of the pristine PP and its composites. At 30% SS loading, composites without maleic anhydride had better flexural strength, 25.3 MPa. Increasing the filler loading above 30%, the flexural strength of the composites decreased. PP/SS/Ma composites had low flexural strength at lower filler loading, but at 60% filler loading, the flexural strength was optimal, after which a gradual decline was observed in the flexural strength. Sakahara et al. 13, reported similar findings where the flexural strength of their composites was higher than that of isotactic polypropylene. This the authors attributed to the particle size of the filler. The higher filler loadings might have reduced the interaction of the maleic anhydride with the hydrophilic polymer and hydrophobic filler, thereby causing a decline in the flexural strength. From Figure 3, the hardness of the composites, both compatibilized and uncompatibilized, steadily increased with increase in filler loading. The presence of BioCACO3 increased the stiffness of the polymer matrix. An opposite trend is observed in the elongation of break.PPcomposites in Figure 4. The uncompatibilized composites had higher elongation at break percentage compared to the compatibilized composites. This indicates that the uncompatibilized composites had better ductility. This might be attributed to the dispersion of the filler within the polymer matrix. Salma et al. 13 reported that the elongation at break reduced with increase in filler loading in EPDM/PP/CACO3 composites. 4.0 Conclusion. Particulate fillers such as CACO3 is used extensively in polypropylene to improve its mechanical properties as well as reduce the production costs. Cockle shell, a bioresource with high CACO3 deposits, has been used in the study in place of mineral CACO3, and the mechanical and physical properties were observed to be better than the pure polypropylene. Incorporating maleic anhydride into the composites of polypropylene/cockle shell boosted the tensile strength and flexural strength, as the interfacial adhesion amid the polymer matrix and the filler was improved. Though at higher filler add-ons, there was a decline in these values. Cockle shell/polypropylene composite is proposed to be used for automobile interior and exterior application and any other suitable applications.